They are no more quantum particles. So you have to remember that condition, which we derived, much less than 1. So the distance between two particles is much less compared to, but in these cases they'll be almost equal. Okay. So now here you can describe particles by x coordinates, x1, x2, so on, xn, and then you can have velocities, un, and then time. So these are basically the various parameters by which these particles can be described. So each time these parameters, these positions will change, velocities will change. Okay. So now instead of Schrödinger's wave equation, you can use Newton's laws. So this is level 2. Now level 1. So level 2 we can describe through distribution function. Distribution function, which is basically given as f of v. Okay. So it's basically velocity, coordinates, and time. So they are the distribution function. Now this will lead to Boltzmann's equation. I don't have place there, but Boltzmann's equation. So similarly, you can go to the next level, level 3. Level 3 is basically a continuum where you can describe any fluid. So in the continuum, you'll not have all these parameters. You'll have just density, which is a function of x. Its density, temperature, velocity, which are all functions of x. Now this is called the hydrodynamic equation. So like that, now you have got 0 level, level 1, level 2, level 3 for the neutral fluid. Similarly, let us write down for plasmas. So for plasmas, what will happen is level 0 and level 1, they are same as the neutral fluid, whereas let us now remove this portion. So level 2, basically we have same the distribution function. In the earlier case, it was basically defined by the Boltzmann's equation, whereas here it will be Vlasov's equation. Vlasov. Vlasov
Sir,
equation. Yeah.
sir, if I may, but the writing on the board is very hazy, sir. We cannot make out, and after the first level, it's not visible on the
Oh,
screen.
okay. So it's too small. Eh? Okay, then I'll just remove this portion. See, 0 level and level 1 for plasma is also same as the neutral fluid. Now coming to the level 2. So level 2, it will be described by a distribution function. In the earlier case also it was a distribution function, but here you will have same f of x, u, and t. Okay, and instead of Boltzmann's equation there, you will have Vlasov's equation. Vlasov. Is it visible now? Glass of.
Yes, sir.
Ah. So now it will not be in the neutral fluid. It was described by the Boltzmann's equation, whereas in a plasma, the same description of particles will be given by Vlasov equation. This will come to as we go further, in the class. We'll see what is this Vlasov equation. We'll try to compare it with the Boltzmann's equation and see how they are different. Okay, so that then the things will become clear how a neutral fluid is described by various theories and how a plasma is described by various theories. Okay. Now, in the plasma, after the level 2, you have a level called level 2.5. So in the neutral, it was 2, and then next level was 3. Whereas here you will have a level 2.5. This is basically described by a two fluid equation. So the most dominant constituents are basically electrons and ions. So you have equations for both the, so there is electron fluid and an ion fluid. And there is an interrelation, they have interactions between each other. So that is how momentum and energy gets transferred from one species to this other species. So you have a two fluid equation. So this is basically level 2.5. After this, you have got a level 3. We'll see what this level 3 is. So level 3 is basically a one fluid equation. So here you don't have an electron fluid and ion fluid separately. So what you have is just the electron fluid. So basically what you are doing is from level 0 to level 3, we are making it more and more approximate. So the model is becoming more and more crude. So that is how, as I told you in the beginning, in my previous lecture, that you are making it crude, but retaining all the physics. Okay, so that is the reason why we are making the level going from level 0 to level 3. We know that we are actually making a lot of approximations, but then it is a useful approximation because you are able to understand the physics. Once you go to the 0 level, you have to take all the particles I told you, every particle, and try to write down the equation of motion for every particle. So how many particles you have? About n, which means 10 to the 13 or 14 particles per cc. So that you have to write per cc. So you have to take the total plasma. Number of particles will be huge. You have to write so many equations. That is 0 level. Which basically, see, finally you have to do that. But then it's a total mathematical game. You will miss all the physics part of it. So therefore, people came up with this levels, where you go for cruder and cruder models, basically retaining all the physics. Okay. So in the one fluid equation, so now you have parameters like rho of x, and then you have got temperature, which is T of x. Then you have velocity, which is u of x. Then you have magnetic fields. Remember, this magnetic field is basically an addition of external magnetic field plus the fields produced by the particles themselves. So self-consistent fields also. You have both the, so that is how you describe, and then take those equations and then see the evolution in time. And this is called the MHD equation. It's a very important model for the plasma. Though it is level 3, still it's called Magneto hydrodynamic equations, which basically tells you about every type of plasma instabilities. I don't know whether I'll have time enough to get into some of the instabilities and show you how MHD equations are useful to describe all these instabilities. But there are certain instabilities for which you may have to resort to kinetic theory. This theory may not be good enough. So you have to go to a level lower, which is the kinetic theory for plasma, not the fluid theory. So you have to go to the kinetic theory to describe certain types of instabilities, which are called two-stream instabilities and things like that. There are lots of instabilities of that kind, fire hose instabilities. Sometimes when I get time, I'll describe to you what kind of instabilities are these, how they are generated, and how they can be suppressed. Okay, but most of the MHD equations can derive most of the plasma instabilities. Only rarely you will have to go into a level lower than this, where you have to describe the whole plasma in terms of kinetic theory rather than fluid theory. Kinetic theory basically means again particles. So essentially what we are trying to do now is the whole fluid now is broken up into fluid elements. Now instead of having a particle velocity, particle v is a particle velocity. Instead of particle velocity, what you will use is u, which is the fluid velocity. So it's a fluid element which has a velocity u instead of vx. So same equations of motions, that m dv by dt is equal to E plus v cross b plus you have all the forces, external forces. It could be gravitational force plus all the forces from the applied forces. Or if you take collisions, you'll have the friction part of it. So that part will also be added, collisions. So this is the equation of motion for each particle. Instead, what you do is you make it for the fluid element, which means the fluid element contains lots of particles in them. So basically, you're now, instead of writing for every particle, you are now collecting few particles together which have the same velocity, because inside the fluid element, all the particles should have the same velocity. And you can now describe a fluid element by the same equation now. Okay. That basically we'll see in our next class, how to start with this equation and then get to other things. Today I'll give you just some summary of it. How so essentially what you will have to do now, after I have described to you all those levels, 0, 1, 2, 3 levels, what you have to finally do in the fluid model for plasma is, so conservation of mass, momentum, and energy. this is step one. Step one in our theory. Now, the second step. Second step will be to describe the evolution of the plasma fluid. Now, those variables are basically density, velocity, pressure, and temperature. So they are gross quantities which describe the whole fluid. So this is step one, step two, and step three is basically now because it's a plasma, it's not a neutral fluid, so it has particles which are charged. So because of that, you'll have to now in these two models, what you have to do is you have to put the Maxwell's equations to close the system. You know? So any mathematical system, you have to close the system, otherwise will have more number of variables, less number of equations. So you'll not be able to solve to get all the parameters. You know? So what you have to do now is you have to couple with Maxwell's equation. This will be step three. And step four is basically now you have pressure. Pressure is coming as one of the parameters. So you'll have to go for a gas equation. P is equal to nkt or something of that sort to basically close the whole system so that no variable is there which is not defined. So the fourth step will be equation of state. Basically, you have to define what is pressure. How is pressure defined? So either it could be if it is a shock wave, the dependence on pressure and rho density will vary. So if it's a normal adiabatic gas, then the ratio is of some type. If it's a shock, it will be a different type. So depending upon the problem, you'll have an expression for pressure, which is basically the equation of state. So that is how you close the whole system now. Now you have system of equations. I described to you all those equations, you know, or conservation of mass, momentum, and energy. And once you have this, you can now evaluate plasma variables like density, velocity, pressure, temperature, things like that. Then couple it with Maxwell's equations, and then equation of state to close the equations. So then you don't have any variable which is not defined. All the variables have to be defined. Otherwise, in the equations, you'll have some parameter which you don't know. So you should not have. Then there will be a mathematical. Your code is not going to solve this because it will not know what is pressure. So therefore, you have to close the equations. So you have to have some equation of state. What your state is defined by what type of pressure density relation. Once that is known, you put that equations, and then now you can all the parameters can be solved. Finally, you'll get a position of the particles, velocity for each time. Basically, it's a time evolution. You're basically trying to track how the particles are moving. In this case, how the fluid element is moving. Okay. So in every fluid element, what will happen is there are momentum and energy getting into the fluid element and some of it leaving it. So you have to balance the two. So that is what you have to do when you do a momentum equation. Same thing you have to do for the energy equation also. Okay. So I think I have just 2 more minutes. So maybe I'll stop at this point. Then maybe next class I can take actual how to solve the continuity equation, and then momentum equation and energy equation. Okay. So did you understand the total game? See what the way I described to you was that you have various levels of theory. Well, zero level basically you have all microscopic particles which are described there by the quantum theory. So their time evolution will be given by Schrodinger's wave equation. Next case, level 1 will be particles, collection of particles, which is described for various coordinate systems, velocities, and for various time. But these equations are now basically Newtonian equations. So that's the level 1. Level 2, what you are doing is now instead of describing each particle, you are now describing a distribution function. So it has collection of particles. That collection of these particles will have a particular distribution. So you must have come across Maxwell Boltzmann distribution. How does it look like? So this is f of v. What is v? So the distribution function is something like that. So this describes you how the particles are distributed in velocity. Velocity is energy. So how particles are distributed with respect to the velocity. So there are more number of particles with low velocities, and as you go to higher and higher velocities, number of particles are reducing. So this is the Maxwell's Boltzmann equation. So something similar. See, Maxwell. As we go forward, we'll see that there are very specific conditions under which a distribution function will go to the Maxwell's distribution. Only when you have collisions. There could be energy transfer in a plasma without collisions. Though we will not be able to discuss that part. See, energy transfer by what you understand is basically that there's a collisions between electrons and ions, and that is how energy is transferred. But you can always have energy transfer between electrons, ions, not by collisions. So these are called Lando damping, which is basically non-linear effects. So we are not getting into that. Otherwise, very interesting phenomena where the particles generate waves inside the plasma. So waves are generated, and then there's an exchange of energy between the waves and the particle. So this process is called Lando damping. If time permits, sometimes I'll discuss this part also, but it will not be part of your course as such. But somebody interested in that part, I can discuss that part, because lots of instabilities, lots of uh, practical uses. Like you must have heard of plasma accelerators. Nowadays you have particle accelerators which work on the basis of plasma acceleration. So that is totally based on Lando damping. There's a wave particle interaction. So you must have seen this surfer, a person who surfs on the waves. So he's gaining energy from the waves. So finally you can have very high velocities. All that energy is transferred to the surfer from the waves. So something similar happens to the plasma particles also. The particles generate plasma waves, and those waves become non-linear and start influencing the particle velocities. So that is the Lando damping. Okay. So very interesting phenomena. And because of this, you must have heard of the Cern Accelerator, the one which is 30 kilometers radius. It covers 3 countries to produce particles, protons of gigavolts energy, GeV, basically to bombard on two protons to break the protons to understand how the particles, what is the construction of a particle, what is there inside the particle. So these accelerators are huge because they produce 5 GeV, 10 GeV, things like that. Now they are planning even 100 GeV protons. But as the energy increases, the size also keeps increasing. But now, if you want particles of very high energy, but you don't have enough space, so in a very small space, I want to get all these energetic particles. So for that, plasma is a very good source. I hope I could. It's a very interesting topic in which I also worked. So where plasma can be used to accelerate particles to GeV, it's a tabletop. It's just hardly a meter. The whole experimental setup is just a meter in which you can produce GeV protons. So this is called plasma acceleration process. And the thing that we take into account is the non-linearity of the wave-particle interaction. So from that we produce waves which are very, very high voltages, which generates very high voltages, and those voltages are required to accelerate the particles. So very interesting physics phenomena. It's called Wakefield acceleration. If some of you are interested, I can send you some information on that. Very interesting. A lot of work is going on in IPR also. Okay, so I think I'll close for today. Any questions or clarification? Please, I want feedback from you people. If there are questions. Okay, if there are no more questions or clarifications required. So Pratik, I'll do one thing. I'll send you the notes on this plasma as a fluid. So you can actually circulate to your other colleagues also. And I'll keep sending you lots of information. Okay, as the time goes on, I'll keep sharing a lot of things with you people. Okay, so now that I have your email ID, so I think immediately after this class, I'm going to circulate the notes to you people. Very simple understanding. You don't have to go through many books. It's actually a essence of all the books, at least 7 or 8 types of books. So I think it will be interesting for you people. If you need to get into more details, probably then you have to go to a textbook.
So,
Yeah, any question? Yeah, Ninan?
Uh, yes, sir. So, I would request you, sir, to provide the students your contact or your email ID at least. So,
Yeah, I have sent everything to Pratik. I've sent my
okay,
email ID.
pass
Okay.
it on the.
So
okay,
I want maximum feedback from you people because see, this topic I'm teaching for maybe the first time, though I keep teaching many other topics in plasma physics. Instabilities and all is my favorite topic. But this plasma as a fluid or waves inside the plasma, maybe 1 or 2 classes I have taken in IPR, but it will be very nice if you people give me feedbacks so that I can improve. Okay? I need this feedback from you people. And plenty of details I can share with you people. So that's it. So any more questions or clarification? Be more interactive there. Don't feel more we interact. I think more I can talk to you people. More message, more information I can pass on to you people. So more you interact, it's better for me
Sir,
and better for you. Okay?
uh, hello.
Yeah?
Yes, sir.
Ninad,
Am I
boliye.
audible?
हाँ. I'm
Yes,
able to
sir.
hear
I
you.
had. I would like to give a little feedback if that would be possible.
Yeah, yeah, please go
Uh,
ahead.
so, sir, as you come from a very experimental side at IPR,
Okay.
and obviously, sir, you have a lot of knowledge about a lot of things.
Okay.
And so, personally, I would appreciate it if you would obviously you have that half an hour for your lecture, but at the end
Okay.
of every lecture, if you could, just give 5 minutes of something extra, like you did in today's lecture, like the concept of Wakefield acceleration,
Oh, okay,
and
okay.
so a simple 5 minute talk, not concerning to the syllabus.
Oh, sure, sure. I think that will
Yes,
be great.
yes, that was quite fun. So
Yeah, yeah.
that's my
You see,
two.
nowadays,
two cents.
like I was telling you about Wakefield acceleration. See, there are lots of medical therapy which require protons of 200 MeV or 500 MeV. So such particles, now will be required for most of the hospitals for cancer treatment. Proton therapy is there, carbon therapy is there. So sometime I can discuss this part also with you people. These are becoming very, very important now. So for that, you need particle accelerators which are compact. I cannot go for accelerator like we have in Cern, which is very expensive. It will be more expensive than the hospital itself. So it is not worth talking about such accelerators with the people in hospital. So hospital needs a very, very small compact accelerator. They don't need very high currents of these particle beams, but they need very high velocities. I'll tell you sometime why such high velocities are required for cancer therapy. And therefore, plasma has given a very, very good lead to this, where you can reduce the size of the particle accelerators. Compact, I told you 1 meter size. I can get particles of protons of say 2 GeV, which is equivalent to what you get from CERN. See, these are very important. Little involved because the technology is little involved because you have to produce a plasma and you have to shoot a laser beam inside that. The laser beams produces the plasma waves and then you send in a particle. Those particles are trapped by these waves and that is how the particles get accelerated. So it's a particle wave particle interaction. It's basically a non-linear process in plasma. So I told you about Lando damping, so where particles can exchange energy without collisions. So these are some of the methods by which energy transfer takes place. So a very important part is basically the Wakefield acceleration. So sometime if I get time, I'll discuss this more in details because this is something which I teach the PDPU students. They're all nuclear engineers, so they need lots of such things. They're not so interested in physics, but I may have to teach little physics to them also. Otherwise, some of the concepts they may not get to it. Like Wakefield acceleration, matlab, I had to tell them what is linear stability, what is non-linear stability, instabilities, how these instabilities trap particles, how energy transfer takes place between waves and particles. So little bit of physics to them, not going into too much details about mathematics. See, once I get into too much of mathematics, then people don't show less interest. So I try to avoid that. Well, of course, the game is totally different with you people. You are physics people. I can take more liberties with mathematics and basic physics theories. Okay. Okay. Then okay, Prateek is one who's going to represent the whole class. So I'll be in contact with Prateek. So anything that I send you, kindly share it with all your colleagues. And anything that they want, they can as well write to me directly. You can pass on my email ID to all your
Sir, I
colleagues.
will pass your contact.
Huh? So let us have more and more interaction with each other. It will be good for me also, and good for you, of course. And any general things that we would, as Ninad was telling, every day I'll pick up something interesting and then discuss with you people, so that that can become a very important thing for. You can write a term paper on that, and that is something which will take you into some big labs, like IPR and all. Once you once the IPR people come to know that you are interested in certain topics and you have done some term paper on that or little bit of research on that, they'll be very interested in getting you people into their projects. So that is one way to make entry into some of the big institutes. Not only IPR, BRC, RRCAT, IGCA, all of them are looking forward to bright students who can think beyond their syllabus. Okay. And then many places abroad, lots of our Indian students are going, many of my students are going abroad for their PhD and other activities. So that can be a good channel of information flow between you and me. Okay. Okay, then we'll call it a day. See you people. I think I'll today I could not inform you people earlier, but generally what I'll do now is one day before itself I'll inform so that you have enough time to plan out. Okay. Generally, I prefer a one-day break so that I can do some preparation myself. It is not just the syllabus, but the other things that I have to discuss with you people. So I have to make a full form the whole lecture in my mind. So for that, I need at least one day gap. So that was the reason why I had asked for alternate days. Okay, then see you people. Maybe Friday we can have, but I'll confirm the date. Okay, and one day before I'll give you the information so that you have enough time for planning. Okay, Janak bhai,
हाँ सर
you can stop recording.
राइट सर राइट सर
और कैसे हो आप लोग?
बस मजे में सर
बहुत दिन हुआ आप लोगों को देखा नहीं हमने.
राइट सर
तो आप लोग रेगुलरली जा रहे हो क्या?
हाँ सर जाना पड़ता है सर हाँ सर
Oh,
yes, sir.
how is Biren? Biren, I think he's busy in the hospital.
हाँ सर उनको अंकल को कुछ है हॉस्पिटल्स में इसी सर वो काम में व्यस्त हैं सर
हाँ, उनका वो ऑपरेशन हो गया क्या?
हाँ हो गया सर
ओके. ओके जनक भाई,